Hey there everyone. So while working on an AI system recently, I ran into an interesting challenge that is speaker verification and identification. So whether it's confirming who's speaking or recognizing one speaker from multiple voices in an audio clip, this is a crucial piece in many AI applications and many AI systems, especially if you're developing one of your own locally. And today I want to share two easy and simple solutions I use to tackle this particular problem. And I'm going to be using the Pyannote embedding model, and I'm also going to be using the Vosk speaker identification model. It's a really small model, just 13 megabytes. And for the Pyannote, they have a lot of models. So they have speech separation model, they have speaker diarization. Just in case you want to actually check out these models, you can just go over to the Hugging Face page and check it out. But today we're going to be focusing on the embedding model, and it's a gated model, as you can see here. So make sure you request for access so you can be granted access to this model, because when we go over to our code, we're going to definitely pull it from Hugging Face. So you would need your API key, your Hugging Face API key. So it's really important you are actually granted access to this particular model. So it's pretty simple and straightforward. And both of these models actually are simple to use and make the whole process really straightforward, even if you're just getting started and you're a newbie like me to the AI space. So you can just set this up in your code base. So it's really, really simple. So if you're actually curious about how to extract speaker embeddings and only transcribe the main speaker's audio data, then stick around. So let's get into the code. So this is our IDE, and we are using PyCharm for this project. And if we go over to our project directory, we're going to see we have 3 folders. Make sure you have your virtual environment already set up. I have mine set up, and as usual, I'm using Python 3.12, and I have different requirements over here, and I have speech recognition, Vosk, PyAudio, Python.env. Since I'm going to be using my Hugging Face API key, I'm going to put it in the .env and load it up in main.py when we are running the code. And I have this, and I have these 3. These ones are actually for Whisper CPP, since I'm running it on my MacBook M1 Pro. So that's just it. And for the directories, we actually have the model directory, which we're going to set it up in a way that Pyannote, the moment it actually pull the embedding model, it's going to save it here. It will save it locally for us. And for the Vosk models, we'll have to go back to our browser and download the Vosk models, but we're going to place them here. And modules contain Whisper CPP, and the models are actually here too. I have base.en here. That's the base English model. I have it down here, as you can see. So that's what we're going to be using. And so for the transcription, I'm going to be using Whisper and Pyannote for speaker verification and then transcription. But Vosk already has a speech to text model, and it also has a speaker identification model. So let's go over to the browser and let me show you how to download it. So here's the browser. So this is the speaker identification model. Like I said earlier, all you have to do is click on it and it will start downloading, and it's going to be a zip file. You have to extract it and place it in the folder, and then you can come up here. You can see the different languages they have. You can go for whatever model you actually want for the speech to text, and since I actually speak just English, basically I'm going to go for the English version. I'm going to go to the top. You can choose this one. This is a really small one, 40 megabytes, and this is a large one. As you can see, you can pick anyone and then download it, and the moment you have actually downloaded it, you can extract it. The main thing is it's going to come in a zip. As you can see over here, it's a zip file, an archive, and the moment you extract it, you take that folder and paste it in the Vosk models. That's how we're going to set it up. So let me just set mine up, and I'm going to show you the project directory again. So as you can see in our project directory, I have Vosk here, and these are the models I actually extracted. This is the speaker identification model. As you can see, these are the files that are within that particular folder. So all you have to do is extract the zip and paste the folder in here, and the folder should contain all this. And if you open up the model, the main speech to text model, it actually contains all this. So make sure you just extract and copy the folder here. So that's how we're going to be doing this. And the next thing we're going to do is create another file, another Python file. We're going to call it stt. Sorry, we do not need to add py. And we're going to have 2 classes in here. And the next class we're going to have is, and as you can see here, we have the Vosk stt and we have the Whisper stt. And for this class, we're going to be handling everything that has to do with Vosk. And for Whisper's stt, we're going to be using whisper for the speech to text. But before we actually do that, we'll have to verify that this is actually the user we are expecting, which means we're going to be using Pyannote for the speaker identification. So let's first of all install all our requirements in requirements.txt. Let's go over to our terminal and we're going to run, hit enter, and this should install everything we have in here. As you can see, we have Vosk here. So let's just speed this up. So it's finally done installing, so let's get started. So just a quick note, I also added the Pyannote and Torch Python packages to the requirements.txt, and let's rerun the installation command. So now that everything is installed, let's go over to stt.py, and the first thing we're going to take a look at is the Whisper STT class. So the first thing we're doing here is setting up our device, and since I'm actually using a MacBook M1 Pro, I'm going to be using a CPU since I do not have CUDA available. So what it's actually doing here is it just loads a pre-trained Pyannote embedding model for the speaker embedding and generates a reference embedding called main speaker embedding from the sample file, as you can see here, Austin.wave, and we have that file right here. So it's basically pulling this from Hugging Face, and like I said, we're going to be using our Hugging Face API key. Make sure you get yours from your Hugging Face profile. So as you can see, it's using auth token because that's a gated model. And at the end of the day, we're going to be saving it in this directory models/Pyannote. We have it here already. So next thing we're going to take a look at is the callback method. Now this function, all it's doing is it processes the audio data it actually gets from the microphone and it's saving it to transcribed audio.wave, as you can see in this section. Now it's sending the transcribe file over to process audio function, and that's where it actually gets the output text. And at the end of the day, we're going to clean the output and we're going to check if we have any artifacts. Like sometimes the Whisper model actually just produces you when you don't say anything. It just says you. So we actually have this check here if it's empty or if it says you. And now we're going to print it out, or you can add whatever you want to add here to maybe utilize the output if you want. So the next function or method we're going to be taking a look at is the listening method. And this is really simple. It activates the microphone, as you can see in this section, and we have the print, say something, so you can begin to talk here. So now we actually define stop listen, which uses the listen in the background function. And since this actually uses thread, we'll still use this here to kill same thread once we are closing our terminal, or we are killing the program this is actually embedded in. So that's something that's really important. So the moment it actually runs into an exception, it kills this function. So that's actually really important to add. So the next method we're going to take a look at is the speaker verified method. Now this method is what actually does the speaker verification or identification. It first creates a speaker embedding from the WAV file that was just created while you were actually speaking, and then it just calculates the cosine distance, and the lower the value, the more accurate it is. So I set my maximum to 0.7. So if it's less than 0.7 in any way, it will return through, which means I'm the one talking. So you can set this to whatever value you want depending on the quality of your audio file, because we're going to listen to the one I actually recorded first. That's Austin.wave. I'm going to take a look at it shortly because that's what we're actually comparing to. We'll always be comparing to Austin.wave, and you see it's not really a high quality audio recording. So but that's what I'm actually using. So let's scroll down. Something we have next is the process audio. Now this is what actually does the transcription. It's really straightforward. I pulled this from, I think, speech recognition library. I pulled this from their GitHub page. So the only thing I added was this part to basically remove unwanted tokens. I just wanted to replace them with just empty strings. The reason why is when I'm actually using a local model, when they actually receive these tokens, things like this, they don't know what they'll say. They'll say something really stupid. So I just added this as an extra line, something to just wipe all this off before returning the process string. That's totally up to you. You can choose to add this or not, but I did add it in mind. So now let's look at our Vosk STT class. While initializing it, we're going to set up the speaker ID. So the next thing we're going to be doing is loading up the model and then the speaker model for the speaker verification. And what we're doing here is continuously listen, or just continuously stream the audio input, and we'll capture the audio input and then process it down here. So while processing it, we'll load our results. So we're going to get our speaker vector if it actually exists, and same thing, we're going to get our text. if it actually exists. If not, it will set it to none. So the first thing we're going to do is check if the speaker vector exists on this line. And this is actually important because we need to verify the user before sending the text over to the large language model. And we're going to send the speaker vector that was generated, if it exists, onto the speaker check method. Now, if both of these statements is true, then we're going to check if our text actually exists. And if it does, we're going to print it out, or you can add whatever you want to add here, maybe to use the text, send the text over to the LLM. So that's what we're going to be doing. And as you can see, this method is going to be used to calculate the cosine distance. And if we go down here, we're going to see the speaker check method. And as you can see, it's accepting the speaker vector and it's calculating the cosine distance. So I set this up in a way that we can actually use multiple speaker embeddings or speaker ID, and it's going to loop through it and then calculate the cosine distance. And at the end of the day, it's going to calculate the mean. So it's that simple. But you can choose not to go through all this hassle, and you can just do this instead. So now that you've done this, you'll be fine. So it's that simple. You get the average distance. You can change this to just distance anyhow. But I set this to less than or equal to 0.6, but I'm going to set this to 0.7, less than 0.7, just like we have in Whisper STT. Now I'm going to change this to, so I'm going to do the same thing for Whisper STT. So we are going to compare both of them. Okay, so we have that. So now that all this is out of the way, now let's go over to main.py and we are going to clear this up. And now let's import the Whisper STT class. We're going to import it from the STT file, and since we're going to be trying out the Whisper STT first, let's just do this. We're going to instantiate the class and we're going to call this again. And this time we're going to be calling the listen method. So before we actually run this, let's preview Austin the Wave in Finder. So this is Austin the Wave. Now let's play it. Whenever you are about to find fault in someone, ask yourself the following question: what fault of mine most nearly resembles the one I am about to criticize? As you can actually hear, it is a very low quality audio. So let's go back to our IDE. So now once we actually run this code, I'll keep talking and we'll see if we get a cosine distance of less than 0.7. And after that, I'm going to play a YouTube video. Someone else will actually be speaking and we'll see if we can get a cosine distance of greater than 0.7. If it does that, then that's a pass. So let's run the code. So as usual, the moment it actually transcribes, it means it actually recognizes the speaker. Hello dear, how are you doing? I hope you're doing good. How are you doing today? Are you doing all right? So now let's play the YouTube video.
A remarkable amount of performance from our hardware, including achieving a scalable logical qubit in our milestone 2. While we've ultimately been limited by quantum coherence times, the length of time qubits maintain their intensity.
As you can see, it's above 1, which means it's unlikely me. Like, it's actually really cool and it's really accurate, which is cool. You can choose to set your maximum to 0.6 or 0.5 depending on the quality of the audio, basically, that you're actually using as your reference speaker or you're using for your main speaker embedding. So just take note of that. So let's close this and we're going to move to Vosk. Now let's instantiate the Vosk class and call the listen function or the listen method. So just to have something to say, I got this small snippet of text from Whisper CPP GitHub page, and this is what I'm going to say for the first time before copying the speaker vector. So since I have this here, let's do this. I'm going to instantiate the class and do the same thing here, call the listen method, and let's run it. Having such a lightweight implementation of the model allows to easily integrate it in different platforms and applications. As an example, here is a video of running the model on an iPhone 13 device, fully offline on device. So that's good. Now we have the embedding. This is what we actually need. This is a speaker vector. Sorry, let's copy this. And I'm going to paste this in here. As you can see, now we have what we actually need. So now I can actually comment this out. Now we're going to do the same thing we actually did while testing with Sparse STT class. We're going to run this and I'm going to just say something and we'll see if it can get something below 0.7, and I'm going to also play the same YouTube video and we're going to see if it will get above 0.7. So let's see how accurate it is. So let's run the code again. Hello there, what is your name? How are you doing? Hope you're doing all right today. Hello, how are you doing today? Where are you calling from? So now let's actually play the YouTube video and see.
Our reality, building quantum computers for otherwise unsolvable problems. We launched our first chip, Foxtail, in 2017, followed by Bristlecone in 2018 and Sycamore in 2019, which powered our milestone 1, the first quantum computer to surpass the best classical supercomputer on a computational task, random circuit sampling. Over the years with Sycamore, we have been able to squeeze a remarkable amount of performance from our hardware, including achieving a.
So as you can see, it's above 0.7, which is really cool. Now I'm actually talking, it should be below 0.7. So how are you doing today? What is your name? Hello dear, how are you? So as you can see, it's actually really, really cool. Now let's close this. So for my final thoughts, I do think if you want much better accuracy when it comes to transcription, then you should go for Whisper, because here we're actually using the base model. If we go over to stt.py, let's go to process audio. As you can see, what we're actually using, we set this to a default of base, the English version. So that's what we're actually using. It's a very small model compared to what we are using here. So you can actually check out the file size here. As you can see, it's 1.8 gig compared to the base model. But when it comes to comparing Pyannote embedding model and Vosk speaker model, I do think both of them do really well and they perform really well, especially since we used a very low quality audio for the reference speaker or the main speaker while testing Pyannote. So I do think both of them actually do really well, and you can actually play around with it yourself and you see. But when it comes to transcription, like I said, I do prefer Whisper, since the base model that's way smaller in size performs way better and is way more accurate when it comes to transcription. So that's just my personal preference, but you can actually play around with it and see if which of them you actually do prefer. And that's the main reason for this video. And since this video is to just give you a starting point, or just propose a simple solution to solving this particular problem of speaker identification and verification, you can try out other solutions, but I think this is the really, really basic and simple one. So make sure you do like, share, subscribe if you haven't. It's really important, especially as we're on our way to our first 1,000 subscribers. That's our first milestone, like I said in my previous video. Hit that bell icon so you get notified whenever I release a new content to this particular channel. Thank you for watching. Have a nice one.